everybody. Thanks. We got a little bit of a late start here. Welcome to Understanding the Impacts and Risks of Building Envelope Upgrades. Bringing it all together, it's March 18th. And this is following up from part 1 and part 2. Love the fade. When we do these webinars, we are grateful to highlight Indigenous examples of Indigenous leadership. And one such is the Nahawk Nation, and they are located in what is now known as Bella Coola. The Nahawk housing specialist and advisor Richard Hall, who has 35 years of building experience as an international red seal carpenter, recently produced the West Coast Building Standard Residential Construction Specifications, and that is a publication that he developed in partnership with RDH Building Science and David Wong Sea to Sky Architecture, and urban ecology with support from BC Hydro, BC Housing, and the province of BC. The West Coast Building Standard incorporates recent building science technology and practices, including energy efficient concepts and reduced embodied carbon levels. And most importantly, the new design featured in the guide complements the cultural lifestyle of the coastal communities. One of Richard's intentions with the West Coast Building Standard is that it can be used as a model that can be edited and adapted to meet each nation's unique needs. So, who are we? The Community Energy Association, or the CEA, is a registered charity and nonprofit committed to accelerating bold action by local governments and Indigenous communities related to climate and energy. We are the only nonprofit in BC focused exclusively on supporting local governments and Indigenous communities on climate and energy activities. We now have over 50 staff located in 27 communities across 5 provinces and territories. We accelerate local action and climate and energy through our collective capacity, expertise, our passion, and our commitment to truth and reconciliation, and the United Nations Declaration on the Rights of Indigenous Peoples, or UNDRIP. But what does this have to do with building better? CEA's work recognizes that the built environment is a main source of community-based greenhouse gas emission, and that action in this sector can only result in significant GHG emission reductions that can enhance community resiliency, energy security, and also increase the comfort, health, and safety of our homes. CEA has been involved in building industry education, capacity building for almost a decade. And on the next slide, we'll showcase some of our current projects. So that's a lot of logos on one screen. Let me tell you a little bit about them. So Building a Legacy, Kootenay Clean Energy Transition, and Retrofit Assist are examples of some of the projects through which we coordinate and deliver a variety of activities supporting contractor capacity development across our province. Building a Legacy North is a collaboration of the CEA and the Canadian Home Builders Association of Northern BC, and it focuses to support the building industry and local governments in the climate zones of Northern BC. My colleague Jenna, who everybody that has taken a webinar through CEA will know and recognize, is my colleague, and she's joining me here today. I'm calling in from Prince George on the unceded territory of the Kootenay, and I'm the Northern Initiatives Coordinator for Building a Legacy. So the Kootenay Clean Energy Transition, or KSAT, assists communities in preparing for a more energy efficient and healthy future by providing high-performance building training and capacity building sessions in the Kootenay and Boundary regions. Retrofit Assist offers a comprehensive concierge service to guide homeowners through that complicated, high-level, often emotional process with optional financing available. The program is currently offered in Rossland, East Kootenay, Kamloops, Whistler, and Squamish. And a key part of this program is enhancing contractor capacity in the retrofit assist communities and onboarding, rather, retrofit assist authorized contractors to complete home energy upgrades. So if you are a retrofit contractor on this call operating in any of those regions, make sure to check out the links. We'll pop them in the chat shortly, and they'll also be embedded in our follow-up email. We cannot surpass the opportunity to thank today's funders and partners, and those logos are on your screen. And lastly, for a full list of upcoming events and webinars focused on high performance building, please visit our website at communityenergy.ca, and we will pop that in the chat also. Next slide, please. So while we're talking about retrofits, another really cool program that we want to let you know about is the Home Performance Contractors Network. So if your clients are looking to access provincial or utility rebates for heat pumps, window or door retrofits, or insulation upgrades, then this is a network rather that enables that, enables your clients to access those rebates. By joining, you'll gain access to industry-specific training, and upon completion of that training, you may qualify for subsidies or to be reimbursed for those course costs, and there is no cost for membership. So if you have any questions about the Home Performance Contractors Network, feel free to reach out to them directly with the email provided on this slide. So before we hand it over to the stars of the show, the people that you actually got up early, brushed your teeth, and made your way here to join us this morning, we just have a few housekeeping items. So CEA is dedicated to offering educational opportunities to everyone, no matter what your current knowledge level of expertise is, what level that is. We prioritize creating a safe and welcoming environment for folks to attend, engage, learn, and there is no such thing as a crazy question or an inapt question. Chances are there are other people on the call that are wondering the same thing. So today's format's going to be a little bit different than previous webinars. So Jeff and James are going to work together this morning because Jeff's had a heck of a morning already. And we're going to provide a brief overview on part 1 of this series, and the building science fundamentals before moving into the more specific case studies, and that highlight the importance of adhering to building science principles. After each case study, we will pause for questions. If you have questions as we go along, feel free to pop it in the chat function, or if you're more comfortable, raise your hand and we can unmute you so you can verbally address Jeff and James and ask your question that way. We'll try to get to all of the questions. Some of them we may leave to the end, depending on how our timing and pace is going, but we will really try to get to everybody. If you're collecting CPDs through BC Housing, we'll be sending confirmation emails to those as long as you stay for the duration of the webinar. So on behalf of Jenna and myself, thank you, Jenna, for the opportunity here. Did I miss anything? Is there anything you need to add before we move over?
No, you covered it all. Thanks, Terry.
You're welcome. And so it is my absolute pleasure to introduce Jeff Kirkpatrick and James Bourget from the RDH Building Science. Jeff is a part-time studies instructor at BCIT's Zero Energy Emissions Building Learning Center, that's a handle, and registered energy advisor actively working in central Kootenay and Kootenay boundary regions. We are incredibly lucky to have James. James, I've had a chance to tour and work with him, an extremely knowledgeable person. So we've got some heavy hitters here this morning, and I really appreciate you joining us. Take it away, gentlemen.
All right, thank you. There you go, Jeff.
Morning, everybody. I want to thank you all for coming today. Appreciate it. Thank you for the wonderful introductions, Terry. Well done. Today's session's in regards to understanding the impacts and risks of building enclosure upgrades. This is part 3, retrofits, bringing it all together. We acknowledge RDH acknowledges the traditional territories of the Sinixt, Silex, and the Kootenay peoples, and the legal jargon regarding continuing education and training purposes. Neither RDH Building Science nor persons presenting the material make any representation or warranty of any kind, express or implied, and blah, 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 blah. As you can follow up on the legal jargon, James. So agenda for today, part 1, part 2 recap, and we're going to go through the building science critical barriers in building a system very quickly because we've now rehearsed it a number of times. And then bring it all together, bird's eye view. Step 1, get an energy assessment, understanding good retrofit approaches, some resources, take note of the resources, everybody, and a discussion at the end for questions. So let's jump right in. Environmental loads and the 5 critical barriers in the relationships. Our exterior environmental loads of water, air, heat, and vapor. That's what our mitigating environmental separation is managing. Air, the air barrier system has a direct relationship with air, heat, and vapor. Air is the Uber ride for heat, sound, and moisture. It has an indirect relationship on water loads within the wall assemblies. Thermal insulation, our second barrier, critical barrier, has a direct relationship with the heat, obviously, and an indirect relationship with vapor control and water loads within the building assembly. Water resistive barrier is the direct relationship with controlling water in our environmental separation, and the water shedding surface also has the direct relationship with managing water loads within our wall assemblies. Who's king? The air barrier system. The air barrier system has, like we say, the direct relationship with air, heat, and vapor, but also the indirect relationship with water. None of the other barriers can have that same relationship. So just to clarify, the 5 critical barriers, the water shedding surface meant to keep 90% of the water impact out of our walls. The water resistive barrier, the final paneling and protection, meant to stop that final 10%. The air barrier system meant to control our airflow through the wall assembly. Our thermal insulation barriers and our vapor barrier are 5 critical barriers to all wall, roof, or foundations.
It's interesting that the air barrier is shown on the outside, but it could also be on the inside. But you need to tape and seal all that polyethylene to make it continuous and airtight. That's why you seal polyethylene.
Fun fact, a interior air barrier by default is a diminishing product. A recent study of 78,000 new homes shows that it is a diminishing air barrier system by 38% in the first 15 years of that home's lifespan. So it will never improve. It will always get worse. So the concept of environmental separation requires 5 critical barriers. And when we apply the 4 Ds of moisture control, we get the 9 considerations, take it to the 9s. So water shedding surface, water resistive barrier, thermal, vapor, and air. And our 4 Ds, deflection, that's our water shedding surface, deflect the water away. Drainage, if it gets in, let it get out. Drying, and make sure that we have drying potential within that assembly for moisture loading. And then durability, I want it to last. If I apply these 4 items to all installs, I will get the best results. So take it to the 9s, an idiom to perfection or to the highest degree. Building as a system relies on 3 key components: the enclosure, our environmental separation, our indoor conditioning, ventilation, and then our heating and cooling conditioning. Those are the 3 critical elements of the environmental separation. Best R value, just to recap, this was from our previous discussion. So if you remember the 1970 Rancher upgrade, so a low-hanging fruit application of simple upgrade is our 6 inches of a new attic insulation, improve the attic R value to R40, improve new windows to R4, gives me an area weighted average or a UA value for that building I've improved the R value by 60% for that assembly. Bring it all together. We've seen the design concept case studies in part 1 and 2. Let's walk through a few building upgrade scenarios to apply what we've learned and dive into the details a bit deeper. It's the fun stuff. So an energy assessment, step 1. So ultimately, I'm not going to read the whole thing for you, but the goal of my role as an energy assessment is to understand what that UA value of the building is. I'm going to take, first step 1 is take elevation photos for documentation purposes of the exterior of the building. Come inside, I need access to all exterior rooms with windows, doors, or penetrations. I'm going to measure and assess all windows and doors as part of that UA value because of the windows being the weakest component. So we want to know what our effective R value of the assembly is. We're going to look at all of the mechanical systems, additional mechanical systems like hot tubs, so that we understand what our loads are on the building, the ventilation equipment, and any other, car chargers or any other relevant load, part of that 2E metric. We're going to do a blower door test as a final step to do the ACH rating on the building. And then you'll get, next slide, your renovation upgrade report, which will summarize existing conditions and what the upgrade performance base would potentially look like. So you see up in the top right corner, your current building rating is 176 gigajoules per year. A typical new house of the same size and age range, so they're all scaled comparisons to the Ontario reference building. The typical new house, if you were to build today, would be a 65 gigajoule usage. If you do all of the upgrades that are recommended in the energy roadmap, you could potentially reduce the consumption of this building to 59 gigajoules a year. These are all general values. It's a bit of a gray, we don't take into account what your occupant loads are specifically. There's a lot of default values, so there's a bit of gray area in these, but they're for comparative purposes. So you actually get 3 items out of a evaluation. You'll get an inner guide label for the as tested conditions of the home performance at that time. You'll get a house as a system report, which will summarize all of the envelope components, mechanical components, and the relationship of what that relates to into the gigajoules. And then your renovation upgrade report, which generally is populated with as many items as possible. Even if they're not in your wheelhouse, it's great data to be able to see that comparative, in that decision-making project. Where do I go next? Go ahead, James. And in applying for rebates, there's a number of programs. These are all clickable links in the provided PDF. So the City of Roslin's Retrofit Assist program, we have the Regional Energy Efficiency program from Nelson, the Canada Greener Homes portal, which will take you to the $40,000 interest-free loan, the Better Homes BC rebates page, which will kind of guide you into all of the other accessible rebate programs. And then there's the Clean BC Income Qualified Rebates program, where you can get up to 100% of your rebate or your upgrades covered. And then just some additional links, the Home Performance Stakeholder Council, as well as the Canadian Association of Consulting Energy Advisors, when you're looking for somebody to come and get that first step done. So let's look at understanding good retrofit approaches on the envelope or environmental separation. But James, so what are we dealing with? These are our intrusive thoughts. As a homeowner, I'm looking at the energy audit recommendations. What should I tackle first? It's a tough question. Once you have all that good data, if I was initially looking at solar and then I get all this data on my envelope performance, might have to change gears and look at other options to get to where I'm reducing my consumption values. As a contractor, when you're driving up to the house, what are the materials and assemblies you're working with? It's the first step as a contractor, many years of just pulling up to the house, and that first 30 seconds is critical to set the tone for the next 3-6 months or whatever that project is. And then what kind of assembly improvements can we make first? And then now, once I've got a renovation upgrade report and I've talked to the energy advisor, consulted with the contractor, it's what are the details? Roof to wall, windows above grade or below grade. Let's get into the details. So add up upgrades, some of our existing conditions, and I can tell you, I see some crazy attics out here in Roslyn Nelson Trail. I mean, I've seen some cedar shavings up in these things. all kinds of stuff. And it's just, nobody pokes their head up there. Nobody looks, but this is this is the hat on your head. You know, I'm going to put a good toque on at this time of the year. You know, it's just the hat that encompasses everything, rises through the assembly. Heated air becomes buoyant and stratifies through the assembly. It's loading against your ceiling plane. Go ahead, James. So what we're trying to illustrate with this side is we're going to see in a number of cutaway views of the building in coming up. So as we can see here, these are side view cutaways of the attic roof assembly, typical condition, low insulation values. As I say, I need my 5 critical barriers for a wall, roof, or foundation. All the same, just turned on its side. So in this case, we attic top up. Is it just more insulation? Good. No, I need to ensure that the critical barriers are there, especially if I'm going to do my attic insulation. That's the time where we can see at the bottom there, my air and vapor are the poly by default in the attic ceiling. If I don't have that poly by default, it's the drywall plane. Insulation top up priorities. Am I going to just add insulation? No, I'm going to air seal first. Critical opportunity, not complicated. You know, down on the eaves are typically difficult to get in there, but the rest of the attic is pretty straightforward. I need to air seal first. It's where I'm going to get the most bang for my buck at that attic up insulation. In the attic example of the attic roof assembly, our water shedding surface being the roof shingles, keeps 90% of the water out. Building paper behind, my water resistor barrier is going to reduce or retard any of the incidental moisture. My fiberglass bat for my thermal insulation, and my poly sheet as my air and vapor barrier by default. So attic air sealing, it's lots of little details, but not difficult to do between sealants, spray foams. We have gun applied sealants that can be sprayed into some of these transition areas, or a flash and fill option on the right side where I use the spray foam application as the consolidator in my attic space. So that consolidates all of the components within the attic. And then I do a loose fill over top of that. So this is what it looks like when I have a good attic insulation assembly. Hard to see, but I've got my attic insulation baffles to maintain my ventilation from the eaves, critical to be able to load the insulation all the way to the top plates. I want that consistent insulation value, especially over top of the attic hatch. It's not a void space. We don't leave that open. Consistent insulation values throughout that attic space. Crawl space, the next place to look. Between attics and crawl space, that's your highest heat loss or conditioning loss within your assembly. So obviously attic first, and then in crawl space. Can I just add insulation to my floor and that be my 6th side of my box and leave it as a vented attic? Sure. Nothing wrong with that if you want all the additional detailing work. The continuity is the crisis. So I've got all kinds of ducting, penetrations, wiring, potentially running through my crawl space. Those all need to be insulated as part of that assembly. Heat flow is path of least resistance. So all of these components, is sheet metal an insulator? Not at all. It's a conductor. So all of that piping would have to be covered, sealed, and then covered in order to maintain that continuity. If I pump, because now that I've conditioned my floor, that attic space is even colder, that ducting running through the attic space, heat flow path is going to release, 60% of that energy before it actually enters the house. Another option would be encapsulate and close your attic, your crawl space. It is now part of conditioned space. Additional storage. FSR is a critical component of today's environment. And for me, it's the most logical plan is radon mitigation. It's, moisture control, it's insulative control, and I don't have all the detail work.
Just have to ventilate the space. Don't forget about that now.
It is a conditioned space, needs to maintain above 14 degrees, and is part of the conditioning. So fully insulate ducts or convert to a conditioned crawl space. I can use XPS, spray foams, a combination in order to get that continuity. And I'm going to want to make sure that I carry it through into the floor headers. Critical continuity. So good retrofits, window replacement. Go ahead, James, just the title page. So typical existing stock home, size and measure all existing windows for replacement. There's a big checklist either within CSA 440 or in the best practices guide for window replacements. At the end, there's a window checklist that discusses what are my exposure ratings, my DRWI, my direct rain and wind exposure index. These are critical components to being a window and recontractor. This is part of the process of assessing what is the best case scenario for this home. So existing conditions, say an aluminum, single pane, old window, or even a double in an existing assembly, and the discontinuity, this is the critical dysfunction of our existing stock homes. We can see here that the dotted line on the left side is our interior control barriers now, are poly by default. And that's not connected to the windows type, in continuity, or my water resistor barrier on the outside. So this is a typical 1970s existing condition, poor performance, speed applied building process. We want to improve that. So remove the windows, cut back the existing assemblies to expose those components, and install the new window. So the first step is obviously to stitch in. James is pointing at the stitch materials, the transition between the existing and new assembly materials. I'm going to put a water resistor barrier and air barrier continuity through the assembly. And I'm going to tie in to my existing air and vapor barrier on the inside of the building. And it doesn't show it here in detail, but that is the critical element. That blue line being my air, vapor, and water control needs to tie into that interior assembly. And this is the biggest default as a post retrofit evaluator. I'm going around seeing good windows installed into openings, but we've not connected the assembly. Because the building performed, prior to, with all of this exhausting energy, drying the building or having some impact on the stabilization of that building. But as soon as we start making changes to the building and the houses and system approach, we have the potential to change the conditions within the assembly. That could increase risk. If I don't maintain, put that assembly back and tie into the critical barriers, I'm putting the building at risk. And one of the mandates of our process is do no harm, is a statement that we use all the time in regards to engineering and consulting, is that we require not to do any harm. So I want to make sure that my installation meets the A440 requirements, and then I'm not doing any harm in the building assembly. So we can see that our continuity through the assembly, at this point now we have a effective water shedding surface on the outside. I've stitched in my materials. I've rod and caulked on the inside to those control layers, and I've maintained subsill drainage out of the assembly. I've taken it to the nines. These are all, that's deflection, drying, durability, right? All tied into this assembly. I've applied it to all the components that went into this assembly to make sure that I always have a back door for any potentials. So any potentials within the window assembly are going to come out the weeps, drain through the assembly. We can see in this picture that our water shedding surface on the outside of the building doesn't need to be a continuous as long as it's positively lapped. Our water resistor barrier is going to transition through the window assembly. So I have a release point for weeps. It doesn't need to be consistent as long as it's positively lapped. But my air barrier, which the window plays a critical component of air, water, and thermal barriers. It is part of the continuity of those systems, especially air and thermal, and need to be addressed as such. So in this case, I have my continuity through the assembly that if I ever did, if I was doing a phased approach, I did my insulation top up and new windows this year, and in 2 years or a year from now, I'm going to come back and address the envelope and improve the envelope performance. I now have the ability to stitch into the existing assembly. I don't have to take these windows out again. This is about renewable details and being able to effectively tie into the existing assembly for future work. So as a contractor, I'm not going to go in there and do a slapdash, slam a window in an opening and don't give a hell about anybody else down the line. A good contractor is going to make sure, just like pool, we put a leave on the ball for the next shot. I'm going to install my window so that I can still utilize that assembly to its full potential. Windows are expensive. I don't want to pull them twice. So here's a sectional view of the head tie-in. So the top of the window, I have my air and vapor control. I have built-in moisture mitigation release points, and I've stitched into my existing assembly. So at this point, I haven't renewed my exterior. I'm utilizing the existing exterior. I've just stitched into it in order for future work. Yeah, go ahead, James. And then the jam view. So we're actually looking at a cutaway vertically, looking down on the jam assembly, if it makes sense. So then we can see that our stitch components are 3-inch wide metal stitching. I'm able to slide it behind the existing building paper, which gives me something to tie into on the exposed area. I can caulk that joint so that I seal between the building paper, that stitch metal, and the cladding assembly. That's the ramp sealant on the left there. So now any incidental moisture that can enter through that trim or assembly of the window can't migrate off to the left to the wall, right? So I've locked out the existing wall assembly, but I've given myself a stitch point so that if I was to come back, I'd remove that existing cladding assembly. I would have something to tie into in future assemblies, but I do have my continuity of that air barrier assembly through to the inside of the building. I've tied into the existing building's air and vapor barrier, and then I've rod and caulked on the inside of the window to maintain that control. And that's a back dam, that's a stop. I put it on the inside because there's potentials that the window itself could fail and I get water in the sill. I don't want to lock it out from the front. I need to maintain good subsill drainage for any incidental moisture within the assembly. We can see here that we're sitting on blocking, and I have maintained good subsill drainage for any potential failures of that window. Take it to the nines. So we can see the rod and caulk. Oh, yeah, carry on. Going to the next phase. So roof to wall transition, this is another critical area as an energy advisor that I'm seeing a weak tie-in consistency. So if I was to upgrade the exterior of this building, I want to ensure that I have uniform continuity with the insulation value. So we can see that the middle of the wall is going to have less thermal conductivity than the top plates in that wall because they're a solid mass. So it's a high potential for condensation for condensing surface. In double digit or when we get down to cold temperatures, I've actually seen interior buildings frost at the top plate perimeter because it's the coldest zone of the wall assembly. It has the least amount of insulation. And typically the insulation is not as pretty as it is in this attic space right now because it usually has wind washing blowing in through the eaves, which pushes the insulation back. So I don't have continuity or a good protection zone at the top plate. So it's critical that my new installation of air and vapor, or my air barrier, or my insulation values, click it forward, James.
Yeah, I'm just going to say that if you're going to put insulation on the outside, you put an air barrier with it. That's just an automatic, okay? And that's what this circle is showing. Here you go.
Huge value. I want to ensure that I carry my insulation to the top plate. So any insulation top-up is going to require insulation baffles in the attic space. We're not showing here, but you can see the dotted line up at the top there. That's to maintain my ventilation rates for an unconditioned attic space. But it is critical that and the reason why the baffle's there is so that I can fill the insulation values consistently right to the eaves. I want as much continuity. If I've got R50 in the middle of the attic space, and I fade out to R20 at the perimeters or less, that's not a good condition. I want to make sure that I've maintained that insulation continuity through the envelope. And then top plate air barrier transition. So typically our interior is poly by default in the plane of the ceiling. So I need to stitch through the top plates for my air barrier continuity, whether that's sealants, tapes, membranes, a range of options to be able to achieve that, but it's not impossible. James and I can speak to the fact that it has been done consistently throughout the history. It's not the end of the world. So we'll look at good retrofits. The Meadow Creek Deep Energy retrofit currently going on. Very interesting case scenario. James, you want to talk this one through? Or?
Sure, I'll talk about this one. It's just down the street from my house, and I just couldn't help get a little bit involved and help my neighbor out. But the assembly is a vertical wood cladding. You can see on the outside, that's a Kootenay house right there. That's a good one. All right, you walk up but to Jeff's point earlier, it says as you walk up to this, what are you thinking? I went, well, I don't know. What's the air barrier on this building? What's the air barrier on the building that you're looking at? What kind of roof is that? You're going to see that when I uncover this, it's a lot of odd things. Like Jeff said, he's seen all kinds of stuff. This is a good example too. Yeah, you see all kinds of stuff. So we got 2x4 walls with crap back insulation. That's with that paper on the backside, a bitumen infused paper that is used for vapor control and draft management. Not so good for air tightness. But a crawl space with dirt floor and cinder block with sporadic insulation on the inside of the block. I mean, a piece here and a piece there. I mean, that's what you got. Metal roofing, venting, no, poorly vented, double blocking, no venting whatsoever. And then they got T&G planking on the inside of the attic. So when you go up in the attic, it's actually got tongue and groove boards all the way across that attic. It was like, so how are you going to chance the air barrier? It's tongue and groove on the top. And then what I found really interesting, what's on top of the tongue and groove, which I'll show you. We got some beautiful single glazed windows, a front porch hat on. So how are we going to get the air barrier around the porch hat on? What are we going to do about that? Do we have to maybe cut it back? That's what we did, but I'll talk about that. And so what is the approach? And what are some of the considerations? And I like this house because it just gets you thinking, what am I going to do? What are those initial thoughts? All right, let's look at it. So they're doing a deep energy retrofit. So we took the inside off. And you think about this, what's the greatest plane of air tightness? Well, they had crap back. So basically there's no air barrier in this building, okay? They had gypsum would have been all that they had from the existing air barrier, be airtight drywall approach, which is an approach, but albeit not a great one, okay? And so what could we do to improve the air tightness on a deep energy retrofit? What's the obvious answer? We'll put the air barrier on the outside, right? But we have to look at what's going on in the inside, and lo and behold, they actually installed the craft backed insulation backwards, and they put the vapor control on the outside. You can see the staining on the back of the gypsum and water staining, and just everything's a little bit odd. You look up into the attic space, the attic's up here. There's no venting into the attic. There's double blocking. So vapor control was on the wrong side of the wall. Staining on the gypsum finishes right there. What's going on? So they went into the crawl space and they installed polyethylene on the floor. And on top of the polyethylene, they're going to put insulation. And they connected that to the block wall with a high performance air sealing tape. And so that was a starting point. We're going to take you from the bottom up. So they've got that happening here. The concrete block there has got a solid core across the top. And so they taped that there, air barrier on the floor, which is the poly doing vapor and air control, brought it up, taped it to the block, okay? The plan for them, like I said, is to put the XPS on the floor. And that's what they're doing now. If you look from the outside, the yellow line shows the air barrier transfer from the inside to the outside. Here's something I'm going to share. As long as you first off, as long as you recognize the air barrier transitions, interfaces, and how they're going to be managed, as long as you do a reasonable effort, you'll always get good air tightness. You don't have to be perfect to get great air tightness, but you got to have a plan. And as long as you address it reasonably, you'll be very well. And this one's ongoing, and we'll talk about that. So that's a transition to the outside. Self-adhered penal stick on the block wall. Okay, so there's a waterproofing on the block wall. Okay, so they're going to insulate the crawl space from the inside and outside. So they're putting 4 inches of mineral wool on the outside of the structure. So you can see that the block wall is going to be insulated on the outside. The floor is insulated on the inside. Okay, they'll also run it up the inside of the block wall and put most of it on the outside, and the block wall could still dry out into that vented space because the top's wide open. Put an HRV in, and they have ventilated into that crawl space. So this is the interesting part. That's the homeowner there. Him and his wife are doing the work themselves. All I did was came down and showed them how to do a window. And then I let him do a window. So I did window number 1. I got him together with a bit of help to do window number 2 and window number 3 and the rest of the project. They needed no further assistance. So getting the guidance to do a good job, it's not difficult to do. It just needs good direction. And they had no issue whatsoever. The windows installed on shims and furring promote subsoil drainage. This was the way a flange window was initially designed to be installed in the best practices building envelope design guide that we authored, 20 something years ago. But now we've gone as humans do, and we just put horseshoe shims up the bottom of the window and call it a day. Window's not going to be totally plumb then. So and that has other effects on hardware and warranties and stuff like that. But again, the homeowner did this, and it's quite simple. And so I don't see the challenges here. We get the contractors out there. Contractors all know how to do this stuff. Maybe it's just some direction. How are you going to put an exterior air barrier in and retain it? That's what the previous slide showed you. You want to put an exterior air barrier on. Windows installed to facilitate drainage, okay? That's what you do. I reviewed once completed, so I popped down because the general store is across the street from their home. So when I go to the store, I can pop over. They did an amazing job. You know, every window looks the same all the way around the entire structure. It's stripped in with purpose. All the paper is exactly the same size. There's formulas for all that once you know the rough opening. It's one of the things that I teach in some of the seminars that we do, is you can pre-cut everything off-site, bring it to site, and install it very quick. Now they're wrapping the building, getting the Tyvek on the structure itself, okay? And all the joints in the Tyvek are taped, okay? To make an exterior air barrier and water-resistant barrier, which ties into the peel stick of the foundation, which then connects across through to the poly on the inside, okay? There you go. Nothing that was too challenging so far, but it's going to get a little more challenging shortly. All we did was the walls, the windows, and the below grade, and having a reasonable plan moving forward. And then we looked at the roof line and said, okay, well, there's nothing here. The double blocking all over the place. But the original building had a flat roof. Well, who knew that? I didn't know that. I thought it was a pitch metal roof. There's no venting allowances through the double blocking. So they put a float metal roof on top of a flat roof. That's what's on the structure. All right, so what are we going to do with that? It became a bit of a challenge, and the attic floor consists of tongue and groove boards. So you can see them on the side here. This is running on the eave side. They run in the direction of the eave, but on each end, gable end, they come out like this. How are we going to transfer an air barrier through that? All things are possible. So we looked at the air barrier transfer, and I talked with the homeowner, and I said, well, let's go up and see your attic. He says, well, there's the attic space. It's got roll roofing on top of tongue and groove boards, and they put in their sloped truss assembly and metal roof over top of it, which kind of interesting. So how are we going to connect the air barrier in the wall to the air barrier in the attic? This is, Jeff brought this up, and I talk with Jeff all the time. And the common theme about that interface connection is always missed. It always is too strong. Most often missed or not addressed. And you don't have to be amazing at it. You just need to do something about it. So on a gable ends, the boards come out. So in the direction, so what I did is we put a membrane across the boards right here, okay? And then where every joint is, you can feel it. We drilled a 1/2-inch hole in every joint all the way along the gable end. And so installed spray foam, a couple passes of spray foam using a froth pack. The homeowner did himself, got a froth pack and figured it out, no problem, got it done, and connected from the top plates to the membrane that's right here. And there's holes drilled in that membrane. So the spray foam goes through the holes to the attic space and then uses all the wood as part of the air barrier transfer between all the holes. Because wood you can use as an air barrier component. We just did that at the top of the wall with the plates and everything else like that, right? So it's the same concept, just carried through. And so we did two approaches. One gable end, we filled the holes with urethane sealant beforehand and put the salvagered membrane on. On the other side, we drilled the holes through the membrane and spray foamed it because I wanted to see on the top side what was the end result. So the second pass installed, here we go, right there. Okay, so one gable end, the boards were injected with sealant, and the other one did spray foam. So I went up and checked it. This is the air seal tape. Here's the urethane sealant that came through the joints, drilled all in each joint, okay? And the air seal tape ran over top of it. And then the polyethylene roll roofing was removed. Polyethylene on the ceiling was connected to the air seal tape, which connects to the wood, which connects to the sealant, down to the underside of the salvagered membrane, which connected to the spray foam, to the top plates, and then the wall membrane came up, it connected to the top plates together. So there's a plan how it all will come together. Went to the other side, said, well, so we put the spray foam, drilled the holes in all the joints and any cracks anywhere. So it's now a continuous line that you can install the air seal tape and connect the poly to that. And we transfer through. Was that hard to do? No. It's a drill bit and a drill. It didn't take very long at all. And now we got continuous receiver tape installed over the holes, and it was taped to it. So here it is when it's done. You can see that for venting, we have established, and we have poly on the ceiling, and everything's taped through, and she's really, really airtight right now. The holes were drilled. I had them drill 2 holes in each of the bays. So now the roof area is vented. That's what the daylight is. Before it was just black. There was nothing. And here's the attic all finished up. Note that it comes up, covers all the cords, and it looks really nice. Here's the inside, okay? And why is the poly not taped? Well, there's a simple answer for that. Because air barriers on the outside. I don't need to tape my poly if I'm doing vapor control, because it's a function of area covered. It's a one-dimensional element. Okay, if I cover the wall 98%, it's 98% effective for vapor control. Okay, well, that's pretty simple to do. And so my air barrier connects from the outside to the air barrier strip into the inside and goes all the way around the building and up over the attic and down in the crawl space. So the retrofit continues. Okay, and we'll see where that goes. It's been left off. It's been winter. We did go try to do some insulation around the window, but 1 hour later, I couldn't move my fingers. So we're just going to let that go for a while. It's warming up now, but I stopped by the other day and he said, I'm just not feeling motivated right now. So I'll go poke him again and we'll finish this story next time if we ever get together again. Okay. This is a good retrofit, a full retrofit. I was involved in this one also. This is a colleague of mine at RDH, and he's cheap. Okay, I'll be honest with you. Okay, as simple as that. So many years ago, his roof there, he says, I need to extend it. So we just put a layer of torch on over top of it, and it worked so good. 10 years later, he still hadn't done anything. I think his wife finally got to him and had to make the home better. It's a 1956 bungalow. Okay, that's it now. So we went from here to here. You notice there's now a closed garage. Okay, the front porch has an overhang, and the wood siding that's here on the building was reclaimed, turned around the other side, which is in really good shape. Okay, and installed on top of the rain screen, and then up above is a cement board stucco finish, which I did for him. It looks like granite, so it looks like an amazing change to the house. Interesting thing with the roof, and we'll talk about it. You see this eave line here, we got traditional gutters on, and it drops down at the eave because 5 inches of insulation were out on the top. So we did a step down on the metal roof back down to the overhang, which is traditional roofing, just metal on the membrane. Again, that was the house beforehand. We made a plan and we got into it, and we started to put 5 inches of insulation on the outside. Okay. And using a thermal clip, which is the yellow things right here, with strapping, okay? And so wood strapping on thermal clips, normally they come with metal. We use wood. There's many ways you can do things. These things work really, really well and are very, very energy efficient. You can also do strapping with long screws only and screw right through the mineral wool, okay? This is interesting because you get the clips and you get the same effect. But that air barrier you see here, the stick VP, this is peel and stick, and please don't be confused about peel and stick is only like blue skin, okay? Peel and stick can also be vapor open and it can also be vapor closed. Be careful of which one you choose. But here you see the air barrier in the wall, and you get up here, how are we going to transfer that across up here? This is the work ongoing. And here's how the air barrier was done. Lo and behold, I don't like spray foam, okay? And I never use it when I have a choice. But sometimes you don't really have a good choice. So if you're going to do spray foam and make this connection very similar to what I did in Meadow Creek, the same thing I did in Meadow Creek, which I forgot to mention, is before I do the spray foam, I run a urethane sealant around all the joints, okay? Because has anybody ever seen foam sort of pull away? And so you can seal all around that and maintain a much better air tightness. If you don't want to do that, that's fine. But these are options, okay? And so with the spray foam goes up in there, you can see that it all gets connected. The air barrier transfers through the plywood because you can't blow air through the plywood up to the membrane on top, which is a cell here membrane, okay? And this original roof is blocked off, okay? It's irrelevant with the insulation up top, okay? The air barrier is up top. That's the key. If you can do this kind of assembly, it's quite risk-free. Again, looking at this high performance windows going in, you can see the insulation and detailing. You kind of got to have a plan, right? How are you going to detail all this kind of stuff? We showed the air barrier connections and all that. Now we've got the thermal. Where's the thermal of the window? It's the window. So you insulate between the window, and you see that the insulation comes right up onto the window frame. You have thermal continuity through the opening. A lot of times you see that dead space around. We're going to put spray foam or great stuff. It's not great stuff. Okay, it's not airtight. Again, here's the reclaimed siding. This was the original siding, flipped around and put back on, which is a great event. And up above, cement board stucco. Here's the roof and the porch being added on. It's a full deep energy retrofit. And here's something really, really interesting, okay? It had this big ugly fireplace, right? So we're doing deep energy retrofit. Do I need this fireplace? No. Did I get another 100 square feet in my living room? We just took this whole thing right out of here and made this now a real living room. We got air tightness and insulation on the outside. We're doing the envelope first, okay? He has forced air heating because he had put a furnace in, so he didn't change that. He doesn't have to use it much now. Here's an aerial view. This is, he's a pilot also, so he likes to fly his plane over the project to see how it's going, right? Being nosy Parker, but it's a cool shot. And you can see the roof assembly going on, insulation and strapping on the roof assembly, and then the metal panels going on. This is the contractor working away on the metal panels and doing all this. So we drew details. You can draw them on napkins, but you got to have a plan. You can see the step down area over the porch. Got the 2-ply on it. That's a nice work area. This is myself. I'm doing a cement board stucco. The homeowner's a bit fussy. He wanted a 1/16 gap around all the windows. And so it was an interesting install, but you can see here the taped off window, but you can see the cement board, the components for the stucco on a thin set system. And then the nice thing about this system is you can each day do a coat. In 3 days, you can be done. Neat way to go. You can see this work is ongoing. Here's when it's finished. It's a heck of a change on a home for a deep energy retrofit. And this is the look of the project when it's completed. And I'll take it back to you, Jeff. Now you're muted again. There you go.
Technical difficulties abounds. No, this is the end. This is actually the end of the presentation. This is just a recap of the links that'll be included in the assembly. Next slide, I think, is just the end and open for discussion, questions. Yep. Any questions out there?
Wow. It's only 8:59. That's amazing, Jeff and James. James, this is the shortest I've seen you wrap up.
Well,
Since
if
we
there's
met,
time for
sir.
questions, yeah.
Yes, sir.
If there's not, there's always time for discussion. And I think I like what Jeff was saying earlier. There's some great things is what are you thinking? Okay, as a contractor, how are you going to deal with a window? My suggestion is if I'm going to put a window in a retrofit, I'm going to do an exterior air barrier approach. And I'll do a range screen exterior air barrier approach that allows any incidental water to drain out over the cladding. Importantly, and I've seen this in projects and talked with Jeff about this, and Jeff has shown me, is sometimes they'll just cut out the window, right? Cut through the siding, cut it out, right? Well, you're going to cut right through that, let's call it building paper, which is your water resistant barrier. So then how are you going to get that stitch back together? And that's what the slides are showing you. Brendan.
Hey guys, yeah, quick question about the Middle Creek house in the crawl space there. So you have the poly barrier, you're doing your vapor barrier inside, and then you have the peel and stick membrane on the exterior. Is the peel and stick vapor open, or does that create a double air barrier? Or sorry, a double vapor barrier in the space?
It creates a double vapor barrier, but the top of the wall is open so it can dry into the crawl space.
Gotcha.
Okay, and so you know what is interesting, and I love your questions, and hell, I love questions, period. But you can have a double vapor barrier if you have no moisture. Okay, that's not a problem. But we left the top of the wall open for any ground or moisture or rising damp that might come into it, okay, that can slowly dry out to the inside of that crawl space. Did not go up and over the whole wall, okay? Left it open as some kind of drying mechanism.
And kind of follow-up question on crawl spaces there. So it's not uncommon to have rubble foundations in the Kootenays. How would you manage that sort of situation?
Well, again, I don't like spray foam, but it's the only thing that's going to get that intimate bond to the rubble, okay? And I was looking at one in Nelson, the same kind of thing, is even a concrete wall. If you put board or anything on that, you have to say to yourself, is that board intimate to that concrete surface? If it's not, there's the potential for condensation to occur because that concrete at the upper parts, and even if it's rubble, is going to be cold because you have exposed foundation on the outside. So you know that's a cold band across your wall, right? So if you have any gaps in there, is it reasonable to consider that conditioned space that you're making, that some of that air can get to that cold space? Yes, and then it will condense. And what does condensed air do? When it condenses, it becomes cold air. What does cold air do? Hot air rises, cold air sinks. So when the cold air sinks in any gaps in that, because the board's not tight, what does it do? It pulls in more air. And what have you done? You've made now a convective loop, a moisture generating machine. That's why basements smell, because they put batten poly and you get that cold air. I've personally gone into basements that said it's leaking, there's moisture in the corner on the floor. That's because two concrete walls coming together. There's enough condensation, it ran down the inside corner, a little puddle. I said, my foundation's leaking. No. So I cut out quickly, big 2-foot chunk of the drywall. And what does the wall look like? Giant drops of water on the wall. I left it off for an hour and everything dried up. That's pretty interesting. So the thing that's interesting, you don't insulate a foundation or basement from the inside. And if you have to, by default on a retrofit, you must get intimacy to that substrate, whatever if it's a formed wall, a rubble wall, whatever it might be, make sure that it's intimate to that there, okay? It's okay to do that. And you don't really have a choice. Make sure that the framing you have is off the wall a little bit to get in behind it so you have thermal continuity, so you don't have a wood on cold concrete, you know, that kind of stuff like that. And you're going to get separation, you spray foam there. You want it behind it, okay? So there's some great work you can do with that. You can put insulation like Jeff showed on the crawl space improvement. You can insulate the floor on top. It's okay to do all that and then put some plywood on top. You got a lovely conditioned space to store stuff, right? Works really good.
Basements are a critical element for insulating. They're between attics and basements, the highest heat loss locations, pressure differential, and convection through the wall assembly is your third. But your basement, it can be up to 40% of your heat loss. So the least expensive, what James described, and intimacy is that key component. The expensive option is you know, underpinning or parging and trying to create that consistent surface within the assembly. So you can go both directions depending on your end result, but the most cost-effective opportunity is to just simply do a 2-inch lift of spray foam to be able to get that continuity, and then you can frame, bat, and build out from there as well. So you doesn't have to all be spray foam, but the critical is I want to connect to the ceiling, to the sheathing of the floor above, because that's where my insulation value on the upper floors are, and I need that consistency come all the way down from the upper floor through the header and into the basement foundation. So consistency, remember, is the key.
You know, if you have a formed concrete wall, you can bring insulation up, right, to the top of the concrete and stop. Then you put insulation on the outside and you come down 4 times the thickness of that wall on the outside past, and you negate that thermal bridge. So, but you have your air barrier on the outside, which connects to the concrete. So you don't need to transfer your air barrier on the inside with spray foam if you don't want to, if you're doing the outside. If you're not doing the outside, then you got to do that because your air barrier is on the inside. You kind of see what we're getting at it, you have, if you get a chance to take the cladding off and do some exterior air barrier and some insulation on the outside, okay? It's, you know, it costs money. Maybe you can't do a lot of insulation, but even 2 inches of insulation will reduce condensation potential within that wall. But you'll get an excellent air barrier. And that's amazing, okay? If you can get 2 layers of 2-inch on, even here in Nelson, you'll survive the average winter temperatures in Nelson. 2 layers of 3-inch, you'll survive -18 design temperatures. You won't have any condensation potential on the wall because the sheeting will always be above dew point. This is the science of it all, right? You don't want to insulate inside only because the sheeting's cold. And any air leakage, because there is some air leakage, will condense on this condensing plane. But if you warm it up, it doesn't condense because above dew point. So the fundamentals are quite simple. And then transitioning air barriers is quite simple too. If it's on the wall, and Jeff said is by default, on the ceiling of any vented attic, that poly is your air barrier. Every time, all the time, all day long. Everybody says big barrier, big barrier. Yeah, that's lovely, but it's by air barrier. How many holes you got through the ceiling? Well, you got lights and everything through ceilings. And then what about each room? How does it transfer the poly from the ceiling in one room to the poly in the ceiling of another room? Well, everybody's seen the framers put those poly flaps between the plates when they build. And nobody cares about them, and they're half hanging out and torn off and everything else. That's how you transfer the air barrier from room to room to room till you get to the perimeter where you transfer to the wall. If you address all of these kind of things, everybody gets exceptional air tightness. And that's one of the things I'll share about, you know, look at the step code and air tightness. If you make an air barrier, you'll be less than 1 every time, no matter on a traditional home, if you have a plan. It's if you don't and you miss transitions, then you get these air leakages of 2 and 3 and 4, and some of these older homes. Jeff, what are you getting for air change rates on some of the ones you're looking
7 to 15 air changes per hour on 20,000 cubic feet. That's 140,000 cubic feet of air that I'm conditioning every hour. Do you wonder why the furnace is coming on every 15 minutes at full send? Right?
What would that look like in the parking lot if I took 140,000 cubes and I stacked them up? It would be like, what's that? Well, that's my air leakage. Oh, did you pay to heat all that? Yes, I did. And I'm going to do it again next hour. It's awesome.
You enjoyed it for 10 minutes and then it went out the bloody windows.
Oh, we've got a hand up. Aaron?
Hey, Jeff and James. Aaron here. So can you guys describe good approaches to insulation and air barrier from the inside for a unvented sloped ceiling in a tiny bathroom with a shower in it? Challenging condition, what would you do?
So if you have, what's your interior finish is gypsum?
It's being torn apart, so it's currently down to studs.
Torn down to studs. So it's
we've got some choices. Cathedral in the bathroom. The bathroom's like 40 square feet. It's tiny.
Right. So you can use an insulation, solid insulation, XPS, and you can put it across the ceiling plane, tape all the joints, and you have thermal and vapor all in one. And then you have to make your connection at your perimeters, which without seeing your project, it's hard to comment, but that's a common approach. And all you do is just put the gypsum right over top of that, and you just use a little bit longer nail, okay? It's a quick, simple one. And you can insulate inside and just put even 3/4 inch, okay? But that's going to be your vapor control and your thermal. It'll add to your thermal. And it's a quick, simple way to get it done.
Yeah, another challenging part I didn't mention is 6.5 foot ceiling height to start and down to 5 feet on the other side. So ceiling height is pretty critical.
And I would suggest back exercises as a starting point. Just saying.
A sunken floor maybe would be nice.
Anyway, okay, so if you add 3/4 of an inch, is that really going to ruin your life?
I agree.
Right. I mean, work on the back. That's all I got to tell you. Back braces are handy. I'm getting old. I got to wear all this kind of stuff. It might even keep you fit too. What the heck?
Nice.
It's just to answer your question seriously, that's a common approach to bring a ceiling plane airtight is using insulation like that, okay?
Perfect, thank you.
Jeff, we have a question in the chat.
Yeah.
Are you looking at that? Yeah,
Yep.
I'm looking at insulating second floor rim joists on a 1920s home. I've got the area open. I'm concerned about interior moisture condensation on the rim joist and causing rot.
Is there existing staining or rot, or is you're just worried about future potentials if you don't do it consistently? Because ultimately, at the end of the day, the moisture within our wall assemblies are a function of air barrier continuity and insulation continuity. All right. So primarily, if my 20 degrees and 40% interior conditioned air can migrate through the wall assembly to my zero conditions, zero temperature on the outside, within that wall assembly is the dew point. At the hygrothermal wall analysis, when I look at the high point of my 20 degrees and 40% inside, the temperature drops as it passes through my wall assembly to eventually a condensing plane, which causes moisture, mold, and mildew. If I can eliminate, so your critical is if you've exposed those areas at the top of your drywall cutout, are you seeing the poly that's in the wall? Which is probably not an effective air barrier, but it is by default your air and vapor diffusion layer. All you're wanting to do is insulate that cavity completely, all the way to the existing wall plane of insulation, and then connect the air barrier vapor diffusion layer within that assembly to the floor above. We call it castling because you're going up and down through the assembly like a castle top, but you're going to want to take that continuity. You're going to seal that poly that's exposed in the wall below to the floor above, if you follow. So you can do that in a number of ways. I tell people, you can use bad insulation to bring the plane of the header out to the wall plane, and then you can cap it with a piece of XBS cut on a 5-degree angle, so it creates a wedge cut right into that opening. So you don't have to fill it all with bat. You don't have to. There's a number of ways to achieve that, but what I want is that continuity from the floor above to the floor below, and then connect that air barrier. The air barrier is going to stop the moisture flow into the wall assembly, and that will stop any potential for mold and mildew.
One thing I would add as a second belts and suspenders type thing, because redundancy is king, is if you can see the poly and your drywall at the top and you see the cut edge of that poly, we showed this on the last webinar, you can use a dust proofing process along that edge, okay? And then you're going to put sealant along that edge to the wood, and then seal inside and castle every transition of your joist to your blocking to your floor with sealant, and then put the insulation in, okay? And do it that way. And then if you can carry it up there with the XBS, you can then tape that also as a double air barrier. Please know you can have 2 air barriers in that space. That's not a problem. But you need to make sure you manage your vapor control into that space and the amount of air leakage into that space. And that'll work quite well. But it is castling. It's a pain to do. But that's the pain of an interior air barrier. If you're on the outside, just go right past it, right?
Cool. Yeah, thanks. That answers most of my question. So yeah, the house, the interior's like it's all lath and plaster. There's no poly air barrier.
Right.
And it's kind of balloon framed, so kind of a lot going on. But so
Your
my
air
goal
barrier,
is
lath and plaster, by the way. Okay, that's your air barrier. Okay.
yeah, I know that. Yeah. I mean, my goal, was just to really reduce as much air leakage into that space as possible. Currently, there's no staining or anything like that, but like it's so leaky that any moisture that would have ended up there would have dried. So yeah, it's just sort of, I think if I can reduce the amount of moisture traveling to it, then I can feel comfortable about insulating it.
Yeah, you make a great point to do inadvertently there. You talked about it's so leaky it dries out. That's how all our older houses worked. But now we want to start we had heat and airflow was our helper, right? And what do we want to do today? We want to keep the heat and we want to keep the air. So we got no helpers. Now we got to use science, okay?
Yeah.
That's the whole thing in a nutshell.
Do you have insulation in the walls, or is it blown in after the fact?
I
What's
have
the
age of the building is about 100 years old. There is some like 2x4 cavities, and there's blown in cellulose. That got added recently, but then it's just trying to figure out what to do on the headers.
And because it's balloon framed, so you've just taken out the drywall in the cavities. Have you come down the wall at all below the floor band so that you're lower and can see all of that in there? Can you see the top of insulation?
Yeah.
Fantastic. That's the first question, is just the box of Rice Krispies and everything sitting at the bottom.
Yeah. So I was able to sort of blow in from the top, taking advantage of the balloon framing. It's just sort of how I cap and close that all off and insulate the rim joists.
So your biggest detraction is the fact that it's balloon framed, so you don't have that continuity through. And so you're worried about those floor bands being a focal point, but the reality is that you're just going to go right by the floor band into the walls above. So is there something holding the insulation above when you cut that out? Is there blocking in the wall or something? What's holding the insulation for the floor above to not just come down the balloon framing?
Oh, it does go down. Like I insulated the ground floor from the second floor.
Right. Okay.
Yeah.
Yeah.
And then I guess once that cavity was full, now I'm sort of the rim joists around there.
The top of the wall?
Uh,
Or is this mid floor?
Sorry,
If
so one
if
of-
you balloon framed, you don't have a rim joist per se.
ledger.
Yeah.
You have a ledger cleat on the inside of the wall sometimes,
Mhm.
but if it's balloon framed, their cavity goes right past the second story floor. Because balloon frame
Yeah.
is stand the walls up and hang the floor in shear on the walls. So I would build my walls in full height, stand the walls up, and then hang my floors instead of stack framing, which is build a floor, run my rim joisting all the way to the outside, build the next wall. Right. So balloon frame means that the walls are continuous from footing to eave, and that the floors are literally hung off of those walls in shear. So when you
Got
open
it.
up that cavity and you say you filled from the second floor down into the wall assembly, you
Yeah.
really don't have a rim joist. So right now you have the only benefit to balloon framing, other than the seismic considerations, is that you have a continuity of insulation through that floor band, right? So
Yeah.
your biggest default in that building is the fact that the air tightness plane, which is your interior finishes by default, that's where you want to find the continuity. So you want to make sure that you seal your lath and plaster to the floors at each level. Any penetrations in that, you need to reduce the air leakage metrics, because that's your only way of mitigating the amount of moisture that's going to get into the wall. There's no such thing as 100% air sealed on an airtight drywall approach, because I have intermediate walls, wiring, ducting, chasing, all kinds of stuff going on. So, I mean, not to be a drag, but interior drywall approach, you'd be lucky to achieve more than 20% improvement in the air tightness metrics. And it's a function of being very diligent. You pull the baseboards off, caulk seal the finishes to the floors, and try and seal up any penetrations, seal up all your switches and plugs on the exterior walls, which are death by 1,000 cuts. And you're trying to mitigate continuity as much as possible. But if you are truly balloon framed, then your insulation value should just carry right through the floor, unless there's some additional blocking or something in the way.
Yeah. Okay, cool. Yeah, that's a lot to think about. Yeah. Yeah, I mean, mostly it's an airtight drywall approach. Just trying to patch. And yeah, I mean, it would be great to pull the siding off, but that's not the plan right now.
Not in these old heritage houses, in
Yeah.
today's marketplace. But if you ever need some specific questions, you can welcome to contact me anytime.
Cool, great.
Send
Thanks,
me
Jeff.
a photo, and and we can hash it out.
Cool, thanks. Appreciate that.
You bet.
But please work on that air tightness, because you answered your own question. Remember, it was heat that would help dry it out. Well, definition of insulation is resistance to heat flow. So you have greatly reduced your drying potential. Make sure you now work your best you can on that air barrier. Okay.
Yeah, we've managed to drop the air leakage from 15 air changes per hour to 9.
Yeah.
So there's still a long way to go. But
That's a big
jump. That's a big jump. Good job.
Yeah. Well done. Well done.
Thanks. Yeah. Cool.
Anybody else? We've got a little bit of time, 10 minutes left before we set you loose. Oh, wait, another message. Here we go. From Elise. How would you manage a semi-enclosed porch over a basement?
First off, you have to consider that the ceiling that is not covered by conditioned space above is what's referred to as an exposed ceiling. So basically it's a roof. So you have to look at it in the from the context that it's a roof, whether it's covered above by an awning or things like that, but it's outside conditioned space. So that is considered a roof. I need all 5 critical barriers and insulation value. So when you refer to how you would manage it, I'm not sure exactly what are you talking about, the insulation values, materials, compositions?
Yeah, I guess we're not entirely sure what the existing condition is. Right now, it's just plywood. That's what we can see as kind of the surface that makes up the, I guess, floor of the porch or top of the roof.
Yep.
And it's semi-enclosed, so there are kind of walls around it, but I guess would we be looking at making drainage outward and treating it like a built-up roof
Yeah,
system?
well, the first consideration from the outside is that that deck, even though it's covered, it should have a membrane, either a roofing membrane or some sort of water shedding, an effective water shedding surface for that assembly. You would want a 2% slope on that deck surface so that you did have water management, a drainage plan. You wouldn't want, if you were ever to wash the building or, there's a probability because it's considered outside. So you want to treat it as a roof. So it would need a roof membrane. It would need a positive slope to manage drainage, whether that's an internal drain or put, best case scenario is just drain it off into the landscaping outside of the building assembly. And then you're going to insulate and have your air and vapor barrier, my thermal barrier in that assembly. So my water shedding surface will be on the outside, which be a form of membrane, roofing membrane, vinyl decking, liquid deckings, whatever whatever the option is. My water resistive barrier, which would be the roofing membrane at the same time. And then my air, vapor, and thermal throughout that assembly. So it is considered an exterior, even though it's vertical, it's considered an exterior element, and that the roof portion of it or the exposed portion that's not covered by conditioned space is considered outside exposed ceiling assembly.
This was a partially covered porch, right, Elise?
No, it's fully covered by the main roof,
But the
and
walls, are the walls open? I mean, is the entire an enclosed porch?
it's nearly fully enclosed. It's like the exterior envelope of the building is kind of the exterior of the porch.
On one side?
So it would have to, like the drainage is challenging because there's not a direct path to drain out. It kind of just goes into there. We'd have to, I guess, open up the walls and create some sort of drainage that goes out to the exterior of the building.
But the walls are continuous then on all sides, correct? The one wall is your building, and then the other three walls are continuous with an entry door on one side?
Yeah, I think so, if I'm following what
Okay.
you're saying.
So
Yeah.
you have water control, everything on the walls. You just don't have any thermal. Your thermal would need to be present on the floor because there's conditioned space underneath it.
Yeah, exactly. Like we don't have water issues. We actually replaced the door recently and there was I was surprised to see there was absolutely no water damage because there's no water mitigation
So
on the floor. But
basically, you have a human garage is what you have, okay?
Well, it's an enclosed unconditioned space. So it's a foyer mudroom type scenario. I thought one wall was open and it just had
one
two
wall is
walls.
open.
Oh,
So the
then-
end wall is completely open, no framing, no nothing.
Yeah.
Okay, so it
Okay.
is totally exterior.
Sorry. Yeah.
What he meant was that three walls were encapsulating and then the building was the back. So it was like a
Oh, I see.
foyer or
No, no.
mudroom. But if one wall is completely missing, no framing whatsoever, and I've got two wing walls surrounding the two sides of the building and the third side being the building itself, then you are technically outside and you just have a large overhang over an entryway.
Mm-hmm.
So either close the wall in or put a membrane down for water.
Yeah.
Right.
You have to treat it as a roof
And then
because it is an exposed element. So typically it would have a waterproofing membrane, a positive slope out that open side of the wall.
Right.
Right.
Yeah.
If you wanted to send me some photos so that I can.
Yeah, I think I'm not doing a great job of explaining it. Yeah.
And I'm picturing 100 different buildings at the same time, trying to imagine what yours looks like. So there's definitely some concerns. You can go some bad directions with this scenario.
Mhm.
So if you wanted to send us some photos and a bit of dialogue, we can look at it a little bit more in depthly to try and identify some
Yeah,
potentials.
that'd be great.
Yep.
Thank you.
That's awesome. Thanks, Elise. Just for the record, I understood exactly what you're talking about. So just kidding. Not
We're
one bit.
without Terry.
Yeah. No, sorry, Jeff. Yes. We have 4 minutes. We have another question,
Oh,
and
yeah.
I'm interested in the answer to this one too. Jeff, what is your view on vapor air barrier paint?
Well, 3 layers or more of latex is a vapor barrier. So all vapor barrier paint is doing is and if you are going to go the vapor barrier paint route, which is nothing wrong with that whatsoever, make sure you read the packaging, follow the mill thicknesses, follow the manufacturer's recommended installation process. Don't just slap it on and think you're done. There is actually a process to confirm that you've met the requirements for that coating, depending on the product manufacturer. But nothing wrong with a vapor barrier paint. 2 or 3, layers of latex is a vapor barrier paint. I've reduced the vapor permeance of that material. So, poly by, 6 mil poly is what, 0.002 nanograms, which is like, we're getting into the quantum scale, right? And so all I'm doing is reducing, simulating a poly barrier or that level of reduced permeance through the material.
The biggest thing that I've found with the vapor retarder paints is what Jeff said. You're not following instructions. See, they're area based. All right. So each liter or quart will cover a certain area. The human given paint always tries to stretch it as far as possible. Okay. That's what you don't want to do. Follow the area coverage and use it in that area, and it'll work fine.
Okay, well, we're not gonna beat anybody up, Jeff. So,
Nope.
James, I think that's good. I think you've done your work here today, this morning, and folks are walking away feeling empowered and more knowledgeable than they did when they woke up this morning. So our goal has been achieved.
Really
Anyway,
appreciate everybody taking their time today as well.
100%. Thank you very much. Enjoy your day. Thank you, James, Jeff, and
Thank
my
you.
colleague, Jetta. Appreciate it. Bye for now, everybody.
Take care, everybody.